Today we're going to be talking about section 1.1, systems of linear equations. Okay, and the way to think about this section is that it's sort of like the road not taken. In my notes I have, what is linear algebra? The road not taken. And that's in some sense true, and in some sense it's not true. In any case, what we're going to show today is sort of like a road not taken. If you go back to junior high school, right, when you're in junior high school, you did something called solving simultaneous equations. Solving simultaneous equations. For example, you were given something like this. 3x plus 5y equals 6, 2x plus 2y is equal to 4, right? You're given two equations and two unknowns, and then you had to solve something like this, right? Back in junior high school. I don't know when you saw this. Maybe when you were babies. Okay. And then you had to solve it, right? And how do you solve something like this? Right. Well, of course, one way you can solve for x, you can solve for y in one of the equations, and then plug it into the other. Right. That's what you did. So typically, what you do is you'd say, okay, well, look, I have to satisfy both of these equations, right? So I have to satisfy this equation, right? And satisfying this equation is the same thing as satisfying this equation, right? If my x and y satisfy this, they certainly satisfy this. If my x and y satisfy this, they certainly satisfy this, right? So you can simplify your equation somewhat. You can solve for, you say, okay, I'm going to solve for my y has to be 2 minus x. And then so I plug that back in, right? And you get 3x plus 5, 2 minus x is equal to 6. And so you get that x is equal to 2, and then y is equal to 0, right? So this is, just to remind you of what you did back when you were kids. Okay. Okay. So maybe at that point, you were given at that time, as I recall, you were given a bunch of equations like this, and you had to solve them, and they always seem to work out, and you always seem to get like x is equal to something and y is equal to something, right? But maybe you felt like making your own problems, and you said, okay, maybe you have something like this: 6x plus 10y is equal to 10, right? So maybe you make your own system of equations. 3x plus 5y equals 6, 6x plus 10y equals 12. Right? So maybe you're adventurous and you think, okay, I'm going to make my own equations, and you start to try to solve them, right? So what happens when you make this system of equations? What would happen then if you tried to solve it? Did anyone see immediately?
Okay.
Don't blurt it out. But go ahead and talk. Read.
6x plus 10y is like proportional to 3x plus 5y.
Mm-hmm.
So if you pick a value for x and y, those two equations can't both be true.
That's right. You'd say, well, if you played around with it for a little bit, you'd say, well, look, the solutions for this one are the same thing as the solutions for this one. Oops. Same as the solutions for this one. Right, so your x and y would have to satisfy this equation, and your x and y would have to satisfy this equation simultaneously, right? And that's impossible. You can't have x and y that satisfy both of these, right? Because 6x plus 10y being 12, prevents you from having 6x plus 10y equals 10, right? So this would have you find that there are no solutions, right? Right? Or if you had something like this, what would happen? What would you get in this case? What would your solutions be, Lizzie?
They're the same line, so it's all solutions.
That's right. So they're the same line. So in some sense, the second equation is redundant, right? The second equation is redundant, and so all you need is any x and y that satisfy 3x plus 5y equals 6, right? In other words, any x and y that lie on this line will do, and so you have infinitely many solutions, right? Infinitely many solutions. Yeah. So it's funny, but when I was in junior high school and saw this sort of thing, after solving so many problems that had one solution, I just assumed that they all had one. They always had a solution, and there was always one solution. But that's not the case, right? You could have no solutions. You could have infinitely many solutions, right? So there's some terminology. So you can have no solutions. No solutions. You could have one solution, and you could have infinitely many solutions. Right? There are basically three possibilities. Right? And this sort of system is called an inconsistent system. And these systems are called consistent systems. Right, so this is a consistent system with a unique solution. It's a consistent system with infinitely many solutions. Okay, and you notice that you couldn't have two solutions. You couldn't have just only two solutions, right? These are the only possibilities. Yeah, Molly.
If you started to incorporate like squares into your equations, can you have two solutions then?
Yes, but we're only gonna talk about lines. So that's part of this thing, the word linear. So yeah, but you're right. Yeah, if you have squares, then you have more than one solution. You could have like two solutions. You could have some number of solutions, some finite number of solutions. Okay. So and this has the geometric meaning, right? You're talking about two lines, and so having no solutions means that your lines are parallel to each other, right? Having one solution means that they intersect in one point, and infinitely many mean that they're the same line. Oops. They're the same line. Okay. Right. Okay. So there's some geometric. There's a geometric interpretation. Okay. So maybe the first thing to notice that the solution set could have particular forms. Okay. Okay. So again, maybe you're back in junior high school and you think, okay, so that was interesting. So another question you might have had back then is, what if you are in higher dimensions? What if you're in higher dimensions? Okay, so you make up some problem for yourself. By coincidence, it happens to be the same one that was done 2,000 years ago in the Han Dynasty, in some old Chinese text. So here's one, sort of famous one from a couple thousand years ago. Okay, so you make up something like this, and you think, okay, how does one solve this? Okay, how does one solve this? You say, okay, well, you make some observations. You make some clever observations, I don't know. So maybe not so clever. So the first observation you make is that changing the order of the equations doesn't change the solution set. Oops. Okay, so so this is kind of a dumb observation, but it would be useful, right? That if I switch the order of two of the equations, that doesn't affect the solution set. 2, multiplying an equation by a non-zero number also doesn't change the solution set, right? Because I'm not changing the solution set. I mean, the equation will look different, but you're not changing the solution. You're not changing what x, y, and z satisfy that, right? If it satisfies this, then certainly it satisfies the equation that I get when I multiply by 2 or multiply by a half, right? Okay. The last one, adding one equation onto another equation in the system, also doesn't change the solution set. Okay. So does that seem reasonable to you? That adding one equation onto another equation doesn't change the solution set? Does that make sense? Well, can somebody explain to me why that's? Can somebody explain to me why that doesn't change the solution set? So let's go back to just the simple one. 2x plus 2y equals 4. Okay, so just an example. So you've got these two equations. You say you got one system of equations. Here's one system, right? And then you say, okay, I'm going to keep the same first equation, but I'm going to add on the first to the second. Okay, and here's another. So is this the same line as this line? No, it's not, right? It's not the same line. But what we're saying here is that you've got these two lines that intersect, and you've got the same first line, but maybe a different second line. However, it doesn't change the point of intersection, right? That's basically what we're saying, that you add the first guy onto the second. You're changing the second line. This is not the same line. It's a different system. But the solution set stays the same, right? So let's think about that, right? So you think, okay, but is it true, right? Is it true? Are the solution sets the same? Are the solution sets the same? So let's call this system 1, and call this system 2, right? And you think, okay, well, if I have a solution to system 1, so say xy solves system 1. Okay. If xy solves system 1, does it solve system 2? Sure. Right? Why, Ali? Well, if you satisfy this and this, you're certainly going to satisfy this, and you're going to satisfy this one because you satisfy both of these, so you're going to satisfy their sum, right? If I satisfy this equation and this equation, then certainly I satisfy the sum of those equations, right? Is that clear? Right? If 3x plus 5y equals 6 and 2x plus 2y equals 4, then definitely 5y plus 7y is equal to 10, right? Is that clear? Anybody confused? Some of you are looking down, you look depressed, or that you're trying to avoid. Yeah, read.
Is this kind of just the same as rule 3? Because if you have a solution...
we're explaining rule 3.
Oh, I meant rule, But I mean, sorry, I got confused. Isn't it like the same as adding a number to both sides of an equation? Like, because say in 3x plus 5y equals 6, both of those sides, when you have a solution, will just be 6. right? Like if you find values that a solution that satisfies that, it's just going to be 6 equals 6, right? If you have the proper values of x and y when you plug in those numbers. So if you add 6 equals 6 to the other equation, it's still going to be a true equation.
Yeah. Yes. Basically. Yeah.
Okay.
Yeah, so,
sorry,
yeah.
I got frazzled.
Yeah. So we're not saying anything deep. We're not saying anything deep. Okay. All we're saying is that if you satisfy this set of equations, then you satisfy this equation, this set of equations. Why? Well, if your x and y satisfy this, they certainly satisfy this because it's the same thing. If your x and y satisfy both of these guys, then they're going to satisfy this guy, right? Because this is just the sum of those two equations, right? And if you satisfy both of these equations, you certainly satisfy this sum. Okay, is that clear? Anybody confused? Anybody confused? Okay. So so what we've seen is that then x and y also is a solution for 2, right? So any solution of system 1 is a solution of system 2, right? And going backwards, it's the same thing. Suppose that x and y solve system 2, right? Then do they solve system 1? Sure, because if you satisfy, if you satisfy both of these equations, then, do you satisfy this one? Sure, because you already did over there, right? Do you satisfy this one? Well, yeah, sure, because you satisfy this, and so you satisfy this minus this, right? You satisfy this minus this, and so you get this equation, okay? So then x and y solve system 1, okay? And so what this pair of observations shows is that any solution of 1 is a solution of 2, any solution of 2 is a solution of 1. So the solution sets are the same. Okay. So yes, they are the same. Okay. So what we're doing right now is trying to show that adding one equation onto another doesn't change the solution set. Okay. Everybody okay? Okay. So let's come back to here. Okay. So we've got this thing here: 3x plus 2y plus z equals 39. Right? We have this system here, right? And what we're going to do is use these 3 observations to change the system. Okay, so we use our observations to simplify the system to one whose solution set is obvious. Okay, so here's the strategy. Right? These are things that you can do without changing the solution set. So you do them, and you change it to something where the solution set is obvious. Okay? But that solution set will be the same as this one, right? Because these things don't change the solution set. Okay? So here's what we do. We say, okay, okay, so I'm gonna do it in a particular way. It doesn't have to be this way, but So say, okay, I start off with my system 3x plus 2y plus z equals 39, 2x plus 3y plus z equals 34, x plus 2y plus 3z equals 26. Okay. And the first thing I do will seem kind of useless. I'm going to switch the third row and the first row. Okay, so I'm going to switch the first row, I'm going to switch with the third row. Okay, so that's legal, right? That doesn't change the solution set, right? So I've got now x plus 2y plus 3z equals 26, 2x plus 3y plus z equals 34, 3x plus 2y plus z equals 39. Okay, so haven't changed the solution set. Okay, now I'm going to okay, so I'm going to do two things sort of at once. So I'm going to multiply the first row by -2, and I'm going to add that onto the second row. Okay, I'm going to multiply the first row by -2 and add it onto the second row. Okay, so my row 2 is going to turn into row 2 plus -2 copies of row 1. Okay, row 2 turns into row 2 minus 2 copies of row 1. Okay, so you get x plus 2y plus 3z equals 26. Negative y minus 5z equals -18. X plus 2y plus z equals 39. Okay. I'm sure some of you have seen this before in high school. If you have, feel free to fall asleep. Maybe that's why some of you are looking down or just like looking kind of bored. That's okay. Right. This is not real math. This is sort of like just calculation. Okay. So in any case, for those of you who haven't seen it before, you see that the system is getting simpler, right? So we're getting rid of one of the variables. We're using this x here to get rid of the x's in the following equations. Okay, and so you do the same thing. Row 3, we're going to turn into row 3 minus 3 copies of row 1, right? And so you get x plus 2y plus 3z equals 26. Negative y minus 5z equals -18. Negative 4y minus 8z equals -39. Okay. Okay, and then, so the system is getting simpler. Now I'm going to use this y here, and I'm going to use it to get rid of the 4y, the negative 4y here, right? So I get x plus 2y plus 3z equals 26. Negative y minus 5z equals -18. And I end up with 12z is equal to 33. Okay, so row 3 turns into row 3 minus 4 copies of row 2. Okay, so just like before, these are not the same planes, right? These are not the same plane. These things are planes in space, right? And we're trying to find the intersection of 3 planes, right? Maybe we've got 2 planes going like this, another one going like this, right? There's going to be one point that lies on those 3 planes, right? These are not the same planes, but the point of intersection, the solution set hasn't changed. Okay, not the same planes, but the solution set hasn't changed. Okay, and you say, okay, well, for this one, it's easy to figure out the solution set, right? You know what z is, right? Z is 33 over 12, right? You plug that back into this one, you can figure out what y is, right? Then so you figure out what z is using the last one, figure out what y is using this one, and then you can figure out what x is using the first one. This procedure is called back substitution. Back substitution. Okay. So you use back substitution to see that z equals 33 over 12, y equals -18, and x is 111 over 12. Okay. So you can solve by using back substitution. So this system is easy to solve. Right? This system, the solutions isn't obvious, but you use your observations to transform it into a set whose solution is obvious. Okay? And you say, well, I didn't change my solution set, so the solutions of this one are the solutions of that one. And so this point here is the solution set for that guy. Okay. Everybody okay? Okay, so we haven't really done anything, and if you're bored, that I'd say that shows a certain degree of good taste. Right? This is not, this isn't really, fascinating. Maybe the only interesting thing is, making, reassuring yourself that adding one equation onto another doesn't change anything. Yes, Ian?
I don't think y and x are correct.
You don't think they're correct? That's possible. Maybe I got them wrong. I'm sorry. Y should be 51 over 12. Sorry. And x, I think, is 111 over 12. Yes, Lizzie?
Could you do this with more than 3 variables?
Yeah. So you can. Now, it may not work out so simply, right? In this case, we got one solution, right? We were able, and you see why we got one solution is because we ended up, our system reduced to this triangular form. Okay, what's called a strictly triangular form. So if your system, however large, reduces to a strictly triangular form, you think, okay, I'm going to get a unique solution, right? But that's not the only possibility, right? You could, again, if you think about it geometrically, you could have all 3 planes be the same plane, right? In which case you have infinitely many solutions. Or you could have 2 planes be the same and the third be different, right? And intersecting. Well, in that case, you've got a line of solutions. Again, infinitely many, but it's just a line rather than a whole plane of solutions, right? Or you could have 3 planes that are all parallel to each other, no solutions. There's more possibilities, right? So, but yes, this sort of procedure, and we'll sort of spell out the general procedure, which is called Gaussian elimination, more clearly in a second, will work.
So if you had 4 variables, then there would be 3D shapes?
Yeah, that's right. So you'd have the intersection of you'd have the intersection of spaces. Okay, so, yeah. So, and you sort of see that there's sort of likelihoods of things working out. So if, for example, you're in two dimensions, and you have 2 lines, right? Well, the chances of you having a solution are pretty good, right? Because the only way you're not going to have a solution is if one guy's parallel, right? So your chances are, basically very, very good that you're going to have a solution. But if you have 3 lines in 2 dimensions, then your chances of having a solution are very small, right? Because you'd have to have all 3 lines hitting the same point, right? And the chance of that happening is small, right? So, so this leads to some terminology. Let me introduce some terminology here. So, first off, terminology. 1 m by n linear system means that there are m equations and n unknowns. Okay, so what we were dealing with just now was a 3x3 system, right? A 3x3. First we had a 2x2 system. Now we have a 3x3 system. Okay. If m is bigger than n, we call it overdetermined. Right? Overdetermined system. Basically, you have too many equations. Right? So that's, for example, you're in space. You're in the plane, but you have 3 equations. Right? So you're overdetermined. Pretty likely that you're not going to have a solution. So solution is unlikely or improbable. Okay. If m is less than n, then It's called underdetermined. Underdetermined, right? So, like, you're in R2, you're in 2 dimensions, but you have only one line. That's great. You've got infinitely many solutions, right? Or you're in 3 dimensions and you've got two planes. That's pretty good. Chances are you're going to have infinitely many solutions, unless they're perfectly parallel to each other. Okay. So, right. So if I had right. So if I had if I were in R3 and had only two planes, right? Like, well, we just get rid of one of our previous planes. Okay. If m equals n, it's called square. And just about its shape. Okay. If in the kth equation, the first k minus 1 coefficients are 0, and the kth coefficient is non-zero, then we call it strictly triangular. Strictly triangular. Okay, so over here, right, you know, the first equation, you know, the first coefficient is non-zero. In the second equation, the second coefficient is non-zero, and the first one is 0. In the third equation, you've got a bunch of zeros, and then you've got the third equations, the third coefficient is 0, right? So this is a strictly triangular system. Is everybody okay? I'm very poor at reading people's expressions, particularly at the beginning of the year. You all are basically blank to me. I have no idea if you're understanding or not understanding. To me, it looks like you're all not understanding. Sort of like this. Close your eyes for a second. Close your eyes for a second. Thank you. I'm going to take a poll. Should I go faster? Raise a hand, raise a finger if I should go faster. Raise a finger if I should go slower. Okay, open your eyes, please. Thank you. Okay, so it's about the right pace then. Okay. Okay. So this third thing, the second thing here, it's just to describe a system that looks like a triangle. Okay. It's just to describe a system that looks like a triangle, right? In the kth, if in the kth equation, the first k minus 1 coefficients are 0, and the kth coefficient is non-zero, we call it strictly triangular. Okay. Okay. And like we said before, we make the remark, if it's strictly triangular, then it has a unique solution. It'll have a solution, it'll have only one solution. Okay. Okay, so another sort of dull observation that we can make is that we could just use the numbers. Right? We don't need to write out the x, y's, and z's every time. You know, we could just write down 3, 2, 1. So here's how we usually do it. We write down the numbers. 1, 2, 3, 26. So you make something called, this is something called an augmented matrix. Augmented matrix. Okay, this part here is called the coefficient matrix. And I should say that I'm always going to abbreviate matrix as MX. Okay, so augmented matrix for your linear system. So you take your system, right, and then you apply those operations to it. Those operations are given the name elementary row operations. Elementary row operations. Okay, so those were that you were allowed to switch. You're allowed to switch rows. You're allowed to multiply some row by a number, right? So you could switch two rows. You could take one row and change it to some multiple of itself, where alpha is some real number, but not 0. Alpha is not equal to 0, right? Or you could take a row and change it to itself plus some multiple of another row. Right? So there were three things that were legal, right? And this is the notation that we'll be using. Okay, the switch, the multiply, taking a multiple of your row or adding a multiple of some other row onto your row. Okay, so there's these three operations that we said were okay, right? And you use them, right? You transform your matrix into something simpler. 2, 3, 1, 3, 2, 1, 26, 34, 39. Right, 1, 2, 3, 26, 0, -1, -5, -18. 1, 2, oops. Not 1, 2, 3, 3, 2, 1, 3, 2, 1, 39. Okay. And then we change this to 1, 2, 3, 26, 0, -1, -5, -18, 0, -4, -8, -39. Right? We kept on going until we got something like this. 1, 2, 3, 26, 0, 1, 5, 18, 0, 0, 12, 33. Okay, and maybe we could have gone one step further to get 1, 2, 3, 26, 0, 1, 5, 18, 0, 0, 1, 33 twelfths. Okay. Okay, so the observation is kind of not that amazing. That you could have just dealt with these matrices rather than with the rather than writing it out. Of course, it's the same thing, right? It's the same thing. This procedure is called Gaussian elimination. So this whole thing here of taking a matrix and transforming it into something. So here's the procedure. This thing is called Gaussian elimination. Gaussian elimination. After the greatest, the person who's reckoned the greatest of all mathematicians, Gauss, who probably did this when he was a baby, in one day. This is not anywhere near the greatest thing that Gauss did, of course. So Gaussian elimination, what you do is you try to get a 1 in as far to the upper left as possible. Okay, so the goal is the goal is basically, the goal is to reduce your matrix to something that looks like 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0. Right? So, this, if you had something like this, then, sorry. Right? If you had some matrix that was ones down all the diagonals, that would be great, right? Or maybe let's say it this way: reduce matrix to upper triangular form, to upper triangular form. That's not exactly right, but it's close enough. Okay, so what you do is you try to get, try to get a 1 in the upper left corner, right? As close to the upper left corner as you can. Okay, so you take your matrix here, and I had this 1 available, so I moved it up to here. Okay, so that was good. Okay, these ones are given the name pivots. Okay, it's a pivot. Okay, and the row, it's called a pivotal row. Okay, so this thing here, called a pivotal row. Pivotal row. Okay, once you have your pivot, then you use it to clear out everything below. Okay, so you use the pivot to clear out, you can use, once you've got that 1 there, you can use it to clear out the 2 and the 3. And that's what we did, right? We used it to clear out the 2, we used it to clear out the 3. This is a 0. Okay, we used it to clear out the 3. Okay. So try to get a pivot in the upper left corner, basically. Use it to clear out below. Okay. Once you've cleared out everything below, well, you try to get your pivot again as close to the upper left as possible in the next row. Okay. So you try to get your pivot here. So you generally you change it to a 1. Okay. So we would multiply this guy by -1. We would get +1, +1, +5, 18. Okay. So you get your pivot. Now this guy is the pivot. Okay. And you use it to clear out below also. Right? So here we use the pivot, clear out below. Okay. You keep on going. So now we've got this thing. We want to make this the pivot. We make it into a 1. We use it to clear out below. There is no below. So that's the end. Okay. So once you get to this, once you've done as much of that as possible, that's the end of the Gaussian elimination. Okay. And you end up with something that's called actually reduced. Sorry, something that's called row echelon form. Row echelon form. Okay, so Gaussian elimination takes your matrix and then reduces it to some simplified form that's called the output of the process is called reduced. It's called row echelon form. Excuse me. Okay, let me give you one to try. Okay, so here it is. 2, -4, 2, -2, 2, -4, 3, -4, 4, -8, 3, -2, 3, -2, 0, 0, -1, 2, and you've got zeros over here. Okay. Okay, so here's an exercise. Try to do that. Take a minute or two and do Gaussian elimination on it and see what you get.
Professor?
Yes.
Just about the alpha, the upgrade of the alpha does not equal 0. What's that? Alpha?
Sorry, this is alpha is an element
Oh,
of the
okay.
real numbers.
Okay.
Is an element of the real numbers. X. Okay, because there's only 1 minute left, let me just do it. So if I were given this and told to reduce it, say, okay, the first thing I want is a pivot here, I want a 1 here. Well, one way to do it would be to just divide the first row by 2. Okay, so just multiply the first row by 1/2. Okay, so the first row turns into 1/2 of the first row. So you get 1, -2, 1, -1, 0. 2, -4, 3, -4, 0, 4, -8, 3, -2, 0, 0, 0, -1, 2, 0. Okay, so now we've got the pivot, right? Now we've got the pivot. And so we use it to clear out, right? So you say, okay, I'm going to take row 2 and turn it to row 2 minus twice row 1. Right? I guess maybe maybe I should have cleared it out while there was still 2. Anyway, it doesn't matter. So, okay, 1, -2, 1, -1, 0. And then this minus that gives me 0, 0, 1, -2. Right? 1, -2, 0. Right? Okay, and then the rest stay the same. 4, -8, 3, -2, 0, 0, 0. Zero, zero, -1, 2, 0. Right. Okay. Right. And then you clear out the third row. You clear out, use the pivot to clear out this thing, and you find that you end up with 1, -2, 1, -1, 0, 0, 0, 1, -2, 0, 0, 0, -1, 2, 0, 0, 0, -1, 2, 0. Okay. So then you say, okay, well, in my second row, I can't get a pivot here. I can't get a pivot here. And this is where I get my pivot, right? I can't, no matter how I switch things around, I can't get a pivot here, right? I don't want to use my first row. My first row that's set. Okay. So this is your pivot, and you use that to clear out the guys below. And when you do that, you see that you get 1, -2, 1, 0, 0, 0, 1, -2, 0, and then it's all zeros below. Okay, and so what you end up with is you end up with an underdetermined system, right? This system is going to be x1 minus 2x2 plus x3 minus x4 equals 0. x3 minus 2x4 is equal to 0, right? So you're in a 4-dimensional space. and you've got two equations in this four-dimensional space. Okay. So, so like I said, sometimes you don't end up with a triangular form, right? Sometimes you don't end up with a triangular form. In this case, and we'll talk about this next time, you end up with a system with infinitely many solutions. Okay, and so we'll talk about how to deal with it next time. Okay, so that's it for today.